Before we move on to talk about curvature, I want to just say a couple of more things about arc length and arc length problems, and then talk a little bit more about smooth functions, because that definition sort of came up in the middle of a problem, and I want to just take some time out and really focus on what that means. But first of all, with arc length, there are three types of problems that I could ask you. I could ask you to find an actual arc length. Your answer in that case would be a number. You would be integrating over some interval from a to b the magnitude of r prime of t. I could ask you to find the arc length function. Now that would be s of t, which is a real valued function. So you'd be finding me a formula for expressing the arc length in terms of t at an arbitrary value of your parameter t. And I could ask you to find the arc length parametrization. That would be r of s, a vector function. Okay. That's where you find the arc length function. It's one-to-one. You solve for t in terms of s, and you plug that into your original parametric curve. If necessary, solving for restrictions on s. Okay. So all of these problems involve arc length. All of them are going to involve integrating the magnitude of your derivative. I have sometimes asked for an arc length parametrization, and people have calculated an arc length. They just change the problem. Okay. You're going to lose a lot of points if you do that. Read the directions carefully. These are very different problems, even though they're all going to involve similar initial steps, finding the magnitude of the derivative and setting up an appropriate integral. Okay. So do be aware that those are very different, although related questions that you could be asked. All right, so I gave you the definition of a smooth vector function, and I sort of threw that in the middle of one of our calculations because a consequence of things being smooth is that that arc length function will be one-to-one. So remember, the definition was that r of t is smooth if two things have to be true. R prime of t is continuous and r prime of t is not the zero vector, ever. Okay. Now, geometrically, these two things together are going to mean that there is a continuously varying unit tangent vector. So t, capital T bar, that's going to be a continuous function, and it will always be defined because, well, it's going to be continuous because it's just r prime normalized, and it's always going to exist because as long as r prime isn't zero, we can normalize it. Okay, another couple of consequences about this is if a curve is smooth, that means it has an orientation. If there's always a vector that's pointing in the direction that it's going, that means our curve is going to be oriented. Okay. And it means that s of t is one-to-one so that we can find the arc length parametrization. Because remember, a step in doing that is this gives you s as a function of t. We need to invert that and get t as a function of x. So the arc length parametrization exists for smooth functions. If your function isn't smooth, that might not necessarily be the case. Okay? The fact that r prime of t is continuous, that's usually fairly easy to spot because a lot of the functions that we work with are continuously differentiable on their domains, and so that's not going to be a big problem. I want to talk a little bit about the significance of r prime of t not being zero. If r prime is zero, that basically means that as I'm drawing the curve, at some instant, I pause. Maybe just for that instant. Now, if I pause for more than an instant, then my arc length function isn't going to be one-to-one anymore. because if I pause for more than an instant, then I'm sitting here, I've traveled the same distance, sitting here, I'm sitting here, my distance that I've traveled hasn't changed, so the arc length hasn't changed. But another thing that can happen if the derivative is 0 is that I could reverse direction. So I could be going in this direction, and then I could retrace the curve in the opposite direction. That often happens when we have a curve that does not have an orientation, and so by not allowing that, we ensure that we do always have an orientation. Now, my curve can be going up sometimes and down sometimes, but it won't suddenly change. It will change in a nice, smooth manner. It won't just be going up and then go down and retrace itself. Okay. It's also sometimes difficult to spot whether something is smooth because this condition is easy to miss at some cases. Let's just say I had r of t is equal to cosine t, cosine squared t, o t cubed. Okay, and I want to compare that to a function that actually looks very similar to it. Let's say r2 of t is sine t, sine squared t, t cubed. Okay. Now, if I look here at r prime of t, I'm going to get negative sine t, negative 2 cosine t sine t, that's just a quick chain rule, 3t squared. If I look at r2 prime of t, I'm going to get cosine t, 2 cosine t sine t, 3t squared. Okay. Now, one of those functions was smooth, one was not. They both have continuous derivatives. R prime and R2 prime are both continuous. But this one is going to be 0 at 0. Okay. 0 is the only number that would make my z component here equal to 0. But at 0, sine of t is 0, and so both the x and y components are 0 as well. So this is not smooth because r prime of 0 is equal to the 0 function. Okay. So when a function isn't continuous, that's very easy to spot. When a function isn't smooth, that's not necessarily easy to spot because these are very nice, continuously differentiable functions, but they are all simultaneously 0, and so this is not a smooth vector function. This function, on the other hand, is smooth because the only value that would make the z component 0 is 0, and at 0, cosine of 0 would be 1, not 0. So this one is smooth. So I just wanted to point that out because it's very easy to spot when a function isn't continuous. Not so easy to spot when the derivative is never 0 because a lot of functions are 0 some of the time. In order for a vector function to be 0, all of the components need to be simultaneously 0. And so you do need to check that condition a little bit more carefully. Okay, excellent. So as we move on, we are going to be talking more about curvature. And when we talk about curvature, that's something that is only defined if I have a smooth curve. We are going to need both of these conditions. For a lot of what we did with arc length, if we had this condition, we were okay. Sometimes we needed this condition, particularly in finding the arc length parameterization. Okay. But generally speaking, we could find arc length and the arc length function even if we had a curve that wasn't smooth, if we had a curve that was continuously differentiable. To find the arc length parameterization, we're generally going to want to have a smooth curve. And to define curvature, which is what we'll do in the next video, we're going to need to have a smooth curve.